For a blockchain to be decentralized, it's crucially important for regular users to be able to run a node and to have a culture where running nodes is a common activity. Hello and welcome to another glorious Tuesday, another episode of Ethereum Audible. This one's going out a little bit late today, sorry about that. But welcome back to where we read the best in Web3 and the Ethereum ecosystem. Last week we were reading about the endgame for Ethereum, and we touched on a few key concepts that this week I want to drill deeper in with another epic and kind of legendary read called The Limits to Blockchain Scalability by Vitalik. There are a few core fundamental articles that Vitalik has written that crystallize a lot of the discussion and trade-offs in the blockchain ecosystem. The limits to blockchain scalability is one of them, why proof of stake is another, why sharding is great, demystifying the technical properties, goes into the blockchain scalability trilemma, roll-up centric Ethereum. I mean, we've covered a lot of these, and today we're going to be covering another one written in May of last year, May 23rd, 2021. By the way, all of Vitalik's posts are on his website, vitalik.ca. It's a great place to plug in your RSS feed, just to kind of stay up to date on what he's publishing. But the limits to blockchain scalability, what we're going to be reading today was inspired by a tweet by Elon Musk that he wrote last year when he sort of started tweeting about crypto all of a sudden, and he wrote about Doge, and the tweet goes, ideally, Doge speeds up block time 10x, increases block size 10x, and drops fees 100x, then it wins hands down. And Vitalik wrote this piece kind of in response to that of what are the limits to blockchain scalability. Over the summer up till today, this topic has gotten a lot of interest based on kind of the larger alternative layer ones that have been coming out, whether it's Solana or Avalanche or Celestia. Binance has been around for a long time. And the question of what the trade-off is when you scale your blockchain, because there is a trade-off. And to Vitalik, just like we were reading in last week's Endgame, it's really, really important. And it all comes down to, unsurprisingly, decentralization and user control of the network. And that's what he dives into in this piece. That's what we're going to be reading. But before we dive in, I would just like to give a huge shout out to Alpe Audio, ALPE Audio. It's an audio course platform for learning on the go, mastering topics in depth from A to Z. You can study all kinds of courses there, from creative thinking, product management, Ethereum Audible, a masterclass in customer lifetime value, a whole marketing track, and how to hack your way to growth with the Entrepreneur's Growth Playbook. All kinds of different courses you can take when you're on the go listening to podcasts. You're sick and tired of listening to Ethereum Audible, you can head over to Alpe Audio and start learning on the go. Every lesson comes with a summary that's written and sent to you. If there are flashcards, further resources, I mean, really everything that you would need to learn things in depth when you're on the train, jogging, shopping, whatever it is. Earbuds are in and hands are busy. That's the idea. So that's Alpe Audio. Huge shout out to them. And with that, let's go. The Limits to Blockchain Scalability, May 23rd, Vitalik, Buterin. Just how far can you push the scalability of a blockchain? Can you really, as Elon Musk wishes, speed up block time 10x, increases block size 10x, and drop fee 100x without leading to extreme centralization and compromising the fundamental properties that made a blockchain what it is? If not, how far can you go? What if you change the consensus algorithm? Even more importantly, what if you change the technology to introduce features such as ZK snarks or sharding? A sharded blockchain can theoretically just keep adding more shards. Is there such a thing as adding too many? As it turns out, there are important and quite subtle technical factors that limit blockchain scaling, both with sharding and without. In many cases, there are solutions, but even with the solutions, there are limits. This post will go through what many of these issues are. It's crucial for blockchain decentralization for regular users to be able to run a node. At 2:35 a.m., you receive an emergency phone call from your partner on the opposite side of the world, who helps run your mining pool, or a staking pool. Since about 14 minutes ago, your partner tells you your pool and a few others split off from the chain, which still carries 79% of the network. And according to your node, the majority's chain blocks are invalid. There's a balance error. The key block appeared to erroneously assign 4.5 million extra coins to an unknown address. An hour later, you're in a Telegram chat with the other two small pools who were caught blindsided just as you were, as well as some block explorers and exchanges. You finally see someone paste a link to a tweet containing a published message announcing new on-chain Sustainable Protocol Development Fund. That tweet begins. By the morning, arguments on Twitter and on the one community forum that was not censoring the discussions are everywhere. But by then, a significant part of the 4.5 million coins has been converted on-chain to other assets, and billions of dollars of DeFi transactions had taken place. 79% of the consensus nodes and all the major block explorers and endpoints for light wallets were following this new chain. Perhaps the new dev fund will fund some development, or perhaps it will just all be embezzled by the leading pools and exchanges and their cronies. But regardless of how it turns out, the fund is, for all intents and purposes, a fait accompli. Irregular users have no way to fight back. Can this happen on your blockchain? The elites of your blockchain community, including pools, block explorers, and hosted nodes, are probably quite well coordinated. Quite likely, they're all in the same Telegram channels and WeChat groups. If they really want to organize a sudden change to the protocol rules to further their own interests, then they probably can. The Ethereum blockchain has fully resolved consensus failures in 10 hours. If your blockchain has only one client implementation, and you only need to deploy a code change to a few dozen nodes, coordinating a change to client code can be done much faster. The only reliable way to make this kind of coordinated social attack not effective is through passive defense from the one constituency that actually is decentralized, the users. Imagine how the story would have played out if the users were running nodes that verify the chain, whether directly or through more advanced indirect techniques, and automatically reject blocks that break the protocol rules, even if over 90% of the miners or stakers support those blocks. If every user ran a verifying node, then the attack would have quickly failed. A few mining pools and exchanges would have forked off and looked quite foolish in the process. But even if some users ran verifying nodes, the attack would not have led to a clean victory for the attacker. Rather, it would have led to chaos, with different users seeing different views of the chain. At the very least, the ensuing market panic and likely persistent chain split would greatly reduce the attacker's profits. The thought of navigating such a protracted conflict would itself deter most attackers. If you have a community of 37 node runners and 80,000 passive listeners that check signatures and block headers, the attacker wins. If you have a community where everyone runs a node, the attacker loses. We don't know what the exact threshold is at which herd immunity against coordinated attacks kicks in, but there is one thing that's absolutely clear. More nodes, good. Fewer nodes, bad. And we definitely need more than a few dozen or a few hundred. So what are the limits to how much work we can require full nodes to do? To maximize the number of users who can run a node, we'll focus on regular consumer hardware. There are some increases to capacity that can be achieved by demanding some specialized hardware purchases that are easy to obtain from Amazon, but they actually don't increase scalability by that much. There are 3 key limitations to a full node's ability to process a large number of transactions. 1, computing power, as in what percentage of the CPU can we safely demand to run a node. 2, bandwidth. Given the realities of current internet connections, how many bytes can a block contain? And 3, storage. How many gigabytes on disk can we require users to store? Also, how quickly must it be readable? Many erroneous takes on how far a blockchain can scale using simple techniques stem from the overly optimistic estimates for each of these numbers. We can go through these 3 factors one by one. Computing power. The bad answer. 100% of CPU power can be spent on block verification. The correct answer is 5 to 10% of CPU power can be spent on block verification. There are 4 key reasons why the limit is so low. We need a margin of safety to cover the possibility of DOS attacks, as in transactions crafted by an attacker to take advantage of weaknesses in code to take longer to process than regular transactions. The second reason is that nodes need to be able to sync the chain after being offline. If I drop off the network for a minute, I should be able to catch up in a few seconds. Third is running a node should not drain your battery very quickly and make all your other apps very slow. And fourth, there are other non-block production tasks that nodes need to do as well, mostly around verifying and responding to incoming transactions and requests on the peer-to-peer network. Note that up until recently, most explanations for why only 5 to 10% focused on a different problem, that because proof-of-work blocks come at random times, it taking a long time to verify blocks increases the risk that multiple blocks get created at the same time. There are many fixes to this problem, but these fixes do not solve the other 4 problems, and so they don't enable large gains in scalability as many had initially thought. Parallelism is also not a magic bullet. Often, even clients of seemingly single-threaded blockchains are parallelized already. Signatures can be verified by one thread while execution is done by other threads, and there's a separate thread that's handling transaction pool logic in the background. The closer you get to 100% usage across all threads, the more energy draining running a node becomes, and the lower your safety margin against DOS. Bandwidth. The bad answer is if we have 10 megabytes blocks every 2 to 3 seconds, then most users have a larger than 10 megabyte per second network, so of course they can handle it. But the correct answer is that maybe we can handle 1 to 5 megabyte blocks every 12 seconds. It's hard though. Nowadays, we frequently hear very high advertised statistics for how much bandwidth internet connections can offer. Numbers of 100 megabytes per second or even 1 gigabyte per second are common to hear. However, there is a large difference between advertised bandwidth and the expected actual bandwidth of a connection for several reasons. 1. Megabytes per second refers to millions of bits per second. A bit is 1/8 of a byte, so you need to divide advertised bit numbers by 8 to get the advertised byte numbers. 2. Internet providers, just like all companies, often lie. 3. There's always multiple applications using the same internet connection, so a node can't hog the entire bandwidth. And 4. Peer-to-peer networks inevitably introduce their own overhead. Nodes often end up downloading and re-uploading the same block multiple times, not to mention transactions being broadcast through the mempool before being included in a block. When Starkware did an experiment in 2019 where they published 500 kilobyte blocks, after transaction data gas costs decrease made that possible for the first time, a few nodes were actually unable to handle blocks of that size. Ability to handle large blocks has since been improved and will continue to be improved. But no matter what we do, we will still be very far from being able to naively take the average bandwidth in megabytes per second, convince ourselves that we're okay with 1 second latency, and be able to have blocks that are that size. Storage. The bad answer is 10 terabytes. The correct answer is 512 gigabytes. The main argument here is, as you might guess, the same as elsewhere, the difference between theory and practice. In theory, there are 8 terabyte solid-state drives that you can buy on Amazon. You do need SSD or NVMe because HDDs are too slow for storing the blockchain state. But in practice, the laptop that was used to write this blog post has 512 gigabytes. And if you make people go buy their own hardware, many of them will just get lazy, or they can't afford $800 for an 8 terabyte SSD, and use a centralized provider. And even if you can fit a blockchain onto some storage, a high level of activity can easily quickly burn through the disk and force you to keep getting a new one. Additionally, storage size determines the time needed for a new node to be able to come online and start participating in the network. Any data that existing nodes have to store is data that a new node has to download. This initial sync time and bandwidth is also a major barrier to users being able to run nodes. While writing this blog post, syncing a new Geth node took me 15 hours. If Ethereum had 10x more usage, syncing a new Geth node would take at least a week, and would be much more likely to just lead to your internet connection getting throttled. This is all even more important during an attack, when a successful response to the attack will likely involve many users spinning up new nodes when they're not running nodes before. Interaction effects. Additionally, there are effects between these three types of costs. Because databases use tree structures internally to store and retrieve data, the cost of fetching data from a database increases with the logarithm of the size of the database. In fact, because the top level, or top few levels, can be cached in RAM, the disk access cost is proportional to the size of the database as a multiple of the size of the data cached in RAM. For example, if the cache is 4 gigabytes, and we assume that each layer of the database is 4 times bigger than the previous, then Ethereum's current 64 gigabyte state would require around 2 accesses. But if the state size increases by 4 to 256 gigabytes, then this would increase to around 3 accesses, so 1.5 more accesses per read. Hence, a 4x increase in the gas limit, which would increase both the state size and the number of reads, could actually translate into a 6x increase in block verification time. The effect may be even stronger. Hard disks often take longer to read and write when they are full than when they are near empty. So what does this mean for Ethereum? Today in the Ethereum blockchain, running a node already is challenging for many users, though it is still at least possible on regular hardware. I just synced a node on my laptop while writing this post. Hence, we are close to hitting bottlenecks. The issue that core developers are most concerned with is storage size. Thus at present, valiant efforts at solving bottlenecks on computation and data, and even changes to the consensus algorithm, are unlikely to lead to large gas limit increases being accepted. Even solving Ethereum's largest outstanding DOS vulnerability only led to a gas limit increase of 20%. The only solution to storage size problems is statelessness and state expiry. Statelessness allows for a class of nodes that verify the chain without maintaining permanent storage. State expiry pushes out state that has not been recently accessed, forcing users to manually provide proofs to renew it. Both of these paths have been worked at for a long time, and proof of concept implementation on statelessness has already started. These two improvements combined can greatly alleviate these concerns and open up room for a significant gas limit increase. But even after statelessness and state expiry are implemented, gas limits may only increase safely by perhaps 3x until the other limitations start to dominate. Another possible medium-term solution is using ZK snarks to verify transactions. ZK snarks would ensure that regular users do not have to personally store the state or verify blocks, though they still would need to download all the data in blocks to protect against data of unavailability attacks. Additionally, even if attackers cannot force invalid blocks through, if capacity is increased to the point where running a consensus node is too difficult, there is still the risk of coordinated censorship attacks. Hence, ZK snarks cannot increase capacity infinitely, but they can still increase capacity by a significant margin. Some chains are exploring this approach at layer 1. Ethereum is getting the benefit of this approach through layer 2 protocols. What happens after sharding? Sharding fundamentally gets around the above limitations because it decouples the data contained on a blockchain from the data that a single node needs to process and store. Instead of nodes verifying blocks by personally downloading and executing them, they use advanced mathematical and cryptographic techniques to verify blocks indirectly. As a result, sharded blockchains can safely have very high levels of transaction throughput that non-sharded blockchains cannot. This does require a lot of cryptographic cleverness in creating efficient substitutes for naive full validation that successfully reject invalid blocks, but it can be done. The theory is well established, and proof of concepts based on draft specifications are already being worked on. Ethereum is planning to use quadratic sharding, where total scalability is limited by the fact that a node has to be able to process both a single shard and the beacon chain, which has to perform some fixed amount of management work for each shard. If shards are too big, nodes can no longer process individual shards, and if there are too many shards, nodes can no longer process the beacon chain. The product of these two constraints forms the upper bound. Conceivably, one could go further by doing cubic sharding, or even exponential sharding. Data availability sampling would certainly become much more complex in such a design, but it can be done. But Ethereum is not going further than quadratic. The reason is that the extra scalability gains that you get by going from shards of transactions to shards of transactions actually cannot be realized without other risks becoming unacceptably high. So what are these risks? Minimum user count. A non-sharded blockchain can conceivably run as long as there is even one user that cares to participate in it. Sharded blockchains are not like this. No single node can process the whole chain, and so you need enough nodes so that they can at least process the chain together. If each node can process 50 transactions per second, and the chain can process 10,000 transactions per second, then the chain needs at least 200 nodes to survive. If the chain at any point gets to less than 200 nodes, then either nodes stop being able to keep up with the chain, or nodes stop being able to detect invalid blocks, or a number of other bad things can happen, depending on how the node software is set up. In practice, the safe minimum count is several times higher than the naive chain transactions per second divided by node transactions per second, due to the need for redundancy, including for data availability sampling. For our above example, let's call it 1,000 nodes. If a sharded blockchain capacity increases by 10x, the minimum user count also increases by 10x. Now, you might ask, why don't we start with a little bit of capacity and increase it only when we see lots of users so we actually need it, and decrease it if the user count goes back down? There are a few problems with this. The first is a blockchain itself cannot reliably detect how many unique users are on it, and so this would require some kind of governance to detect and set the shard count. Governance over capacity limits can easily become a locus of division and conflict. Second is, what if many users suddenly and unexpectedly drop out at the same time? Third, increasing the minimum number of users needed for a fork to start makes it harder to defend against hostile takeovers. A minimum user count of under 1,000 is almost certainly fine. A minimum user count of 1,000,000, on the other hand, is hardly and certainly not. Even a minimum user count of 10,000 is arguably starting to get risky. Hence, it seems difficult to justify a sharded blockchain having more than a few hundred shards. History retrievability. An important property of a blockchain that users really value is permanence. A digital asset stored on a server will stop existing in 10 years when the company goes bankrupt or loses interest in maintaining that ecosystem. An NFT on Ethereum, on the other hand, is forever. But once a blockchain capacity gets too high, it becomes harder to store all that data, until at some point there's a large risk that some party of history will just end up being stored by nobody. Quantifying this risk is easy. Take the blockchain's data capacity in megabytes per second and multiply by 30 to get the amount of data stored in terabytes per year. The current sharding plan has a data capacity of 1.3 megabytes per second, so about 40 terabytes per year. If that is increased by 10x, this becomes 400 terabytes per year. If you want the data to be not just accessible, but accessible conveniently, we would also need metadata. So make that 4 petabytes per year, or 40 petabytes after a decade. The Internet Archive uses 50 petabytes, so that's a reasonable upper bound for how large a sharded blockchain can safely get. Hence, it looks like, on both of these dimensions, the Ethereum sharding design is actually already roughly targeted fairly close to a reasonable maximum safe values. The constants can be increased a little, but not too much. Summary. There are two ways to try and scale a blockchain: fundamental technical improvements and simply increasing the parameters. Increasing the parameters sounds very attractive at first. If you do the math on a napkin, it's easy to convince yourself that a consumer laptop can process thousands of transactions per second, no ZK snarks or rollups or sharding required. Unfortunately, there are many subtle reasons why this approach is fundamentally flawed. Computers running blockchain nodes cannot spend 100% of CPU power validating the chain. They need a large safety margin to resist unexpected DOS attacks. They need spare capacity for tasks like processing transactions in the mempool, and you don't want running a node on a computer to make that computer unusable for any other applications at the same time. Bandwidth similarly has overhead. A 10 megabyte per second connection does not mean you can have a 10 megabyte block every second. A 1 to 5 megabyte block every 12 seconds, maybe. And it's the same with storage. Increasing hardware requirements for running a node and limiting node running to specialized actors is not a solution. For a blockchain to be decentralized, it's crucially important for regular users to be able to run a node and to have a culture where running nodes is a common activity. Fundamental technical improvements, on the other hand, can work. Currently, the main bottleneck in Ethereum is storage size and statelessness, and state expiry can fix this and allow an increase of perhaps up to 3x, but not more, as we want running a node to become easier than it is today. Sharded blockchains can scale much further, because no single node in a sharded blockchain needs to process every transaction. But even there are limits to capacity. As capacity goes up, the minimum safe user count goes up, and the cost of archiving the chain and the risk that data is lost if no one bothers to archive that chain goes up. But we don't have to worry too much. Those limits are high enough that we can probably process over 1 million transactions per second with the full security of a blockchain. But it's going to take work to do this without sacrificing the decentralization that makes blockchains so valuable. All right, that was the limits to blockchain scalability. And I hope by now that you can formulate the answer for Elon Musk's tweet, which is why we can't just 10x the block size, 10x the transaction volume, and lower fees by 100x. We didn't get into why lowering fees is a problem or not, but we did touch on the first two parts, which is why you can't just increase the block size and increase the transactions per second. And the answer, beyond all of the mishmash on how we get there and how we calculate in the megabytes per second and computation and storage and all of that, which is pretty technical and I'm not sure how well it translates into audio, but the main point is that we want to make running a node easier. And why do we want to make running a node easier? Because, and it's in this sentence at the end of the article in the summary, quote, "For a blockchain to be decentralized, it's crucially important for regular users to be able to run a node and to have a culture where running nodes is a common activity," end quote. And it's because of that sentence that we want to make running a node easier and not just count on Moore's law and the fact that computers are improving and hopefully my laptop in a year will be able to process the audio for this podcast faster. No, we don't want to overbear that computer, that laptop in a year and just create larger nodes knowing that semiconductors will improve. That's not the goal. The goal is to bring the cost of running a node down, whether that cost is in actual money or in technical capability or in the just kind of the friction of running it on your own laptop. I can run a Bitcoin node on my laptop. I, in fact, do. I don't run an Ethereum node on my laptop, and that's a problem. We need to get it to the point where I can run an Ethereum node on my laptop while I'm recording this, because that's when we know that the network is decentralized. And this, I think, was like the main point that it's kind of subtle and a lot of people miss when it comes to decentralization. And this is just the most common today in the layer one discussions on what is decentralization. And I've heard this come up a lot when the Solanians and Ethereans argue. And when the Solanians put forth their argument on what is decentralization, they define it as the ability for the chain to kind of resist censorship. And for me to know if I was running a node that I have a valid kind of blockchain history. They don't categorize it as us, the individual users who use Solana, we are able to verify the blockchain. They don't categorize it that way. For Anatoly from Solana, and this, by the way, this is perfectly valid for Solana and kind of the blockchain that he wants to create, and which is like a blockchain to run like run like NASDAQ. I think that's the pitch on the deck. A blockchain at NASDAQ speed for high frequency transactions and trading and things like that. But for me, Yoshua, if I was participating in Solana and I can't run a node, and I'll never be able to run a node. If the 300 validators all of a sudden decided to, change the rules of the system for any reason, maybe just like NASDAQ and New York Stock Exchange and the FTSE and whatever, they get acquired and there's M&A and they become an oligopoly and they want to change the rules and increase transaction fees or I don't know what, they could do that and I would not be able to do anything about it. Because I can't run a node, because I can't participate in the system. And Vitalik in the beginning of this article basically lays that out, which is the scenario of what if you woke up in the middle of the night and all of a sudden there was a fork and all of a sudden the big boys decided to give out something to their cronies. Not a crazy scenario, right? Whether that's from like the scenario I just laid out or regulation. All of that could happen. What can I do as a personal user? Will I even know? Will I even know that the rules have been changed? Today, in our modern democracies in the West, we don't know that the rules are changed. There's lobbying. There's like this is what the lobby world does in the centers of government. They put in changes, amendments to the law that the average person never reads, never hears about. And the same thing can happen in large blockchains when you don't run your own node, when you don't verify what's going on. And that's the idea behind decentralization. That's the barometer. That's the scale. That's what we should be caring about as individual users of blockchains. That we should be able to know when the rules of the games get changed and vote with our node and say, hey, no, that's an invalid change. Today we can do that on Bitcoin. That's what the blockchain block size war was all about. Individual users' nodes saying, nope, our node will not accept this new change. We will not process those transactions. And it worked, but it only worked because enough people, there's enough of a culture in Bitcoin of running your own node. And we need that to be available in Ethereum. And it's great that Vitalik has this front and center and that the Ethereum Foundation and everyone who's working on clients has this front and center. And we just need to get there. And then we need to develop this culture of running nodes because without that, we'll never be able to know when our blockchain gets hijacked. So that was the limits of blockchain scalability. And that's why there are limits to blockchain scalability because the trade-off is just too big. When you give away that decentralization, you give away the entire system, especially for a blockchain like Ethereum that powers all of DeFi. That's not the case for a blockchain that runs games or a blockchain that runs music or something else that's less critical. But for Ethereum, where you want to have the decentralized web and you want to empower Web3, we need that level of decentralization. Otherwise, there's nothing here. I think next week we're going to take a little bit of a shift off, and I'm also going to be testing out a new format called Blockchain Bites that are just going to be short little takes on different topics or anecdotes in Web3 and blockchain, kind of short 3-5 minute little segments about, proof of stake or specific takes that I hear that week that I kind of want to opine on. And those will be coming out also on a weekly basis, probably not on the same day. That's it. Happy to hear thoughts, feedback, articles. You can hit me up on at Ethereum Audible on Twitter or at YahooCL on Twitter. Have a great week and let's go.